Okay, it seems that we are live. So, thank you very much for joining me. Okay, we are giving a few minutes. We are giving a few minutes to a couple of minutes before starting. We're giving 3 minutes before we have 3 minutes before the official start of the live stream. So we are giving some time for the people to join. So this is the second experimental live stream, and today we will talking about a subject that is hardly touched on YouTube, as usual, I suppose. And then we'll have some time for Q&A. Okay, I see the first people actually connecting, and this is great. So welcome. We are waiting a couple of minutes to give time to the people to connect. Unfortunately, I couldn't schedule the live stream, so people didn't have the possibility to connect early, and this is the reason why I started a couple of minutes early to give people the possibility to connect. This is still an experimental live stream, one that was not supposed to happen, but I will explain everything in a minute or so. Hi all from the sunny England. So hi Polly, hi Hadu, hi Mark, hi Alexander, hi Vishal, hi Antoine. Alexander's always here. Thank you very much. Hi Antoine, hi Muhammad, hi to hi, good evening Arniban. Where you are? Because you are in the morning. Okay, that's fine. Okay, just let's give people 30 seconds again more to join the live stream. So we're nearly there. Okay, I believe we can definitely start. It's time to start. So welcome to Millennium 7 Star, the channel that helps you make sense of military history and military technology. And please stay with me till the end, because at the end there will be some Q&A, but before there will be something quite interesting. But let's start from the beginning. I wasn't planning to do this live stream, which is largely experimental like last week. This is happening because this week has been one of the most, I can't find correct objective, but it's been a very busy week for me with the number of issues that came up. And so I couldn't work on a specific video. What I could do is put together some documentation to go through aeronautical structures, because this is something that you never hear about. Everybody's talking about the technology, the engine, the aerodynamics, the stealth, and all these kind of things about the planes, but nobody explains you, or it's very hard to find a video or documentation that explains you how the structure of a plane is actually made. And again, it is one of the unsung heroes of aviation, because, for example, the useful lifetime of an airplane depends largely on the design of the airframe and the possibility to do some maneuvers and operate from carriers, operate from, for example, unprepared runways, is something which is, let's say, actually depends on the design of the structure. So structural design is important, is very important, and define the plane in a way that is not less important than propulsion, electronics, or aerodynamics. So we are doing this for about half an hour, 40 minutes or so, and then we will have some room for the usual Q&A where you feel free to ask, well, pretty much anything. We will be doing this live stream with the help of a book that now I will show you. This book, Richard Shevell, Fundamentals of Flight, Prentice Hall. This is a rather old book. Am I suggesting it? Well, it is not. It's difficult to find now. It's not the newest, but it is a good book. The principle that is actually describing hasn't changed. So I took a lot of pictures that I'm going to show today from this book. If you want to, this is not sponsored, by the way. So it's not a bad book to start, but today there's probably something better. So this away for a second, and let's start from here. I am sure you have seen this kind of drawings a lot of times. This is the common structure of a plane. As you can see, there are some elements that are easily recognizable, and I'm sure you've heard at least the names a few times. Starting from the wing, which is the most important part of the aircraft, it's not the fuselage, it's always the wing. You can have the ribs, you can have the spars, and parallel with the spars, you have some stringers are called here, but also called stiffeners. And there is also, obviously, there's also there are plates cladding the plane, cladding the wing, closing the wing, and normally this structure is not visible. On the fuselage, well, it's something similar. In the place of the ribs, you have bulkheads, but they have pretty much the same function. And you may have fuselage spars, but also fuselage stiffeners. And as you can see, the structure in the horizontal plane, in the tail planes, horizontal and vertical planes, in the tail planes is pretty much similar to the structure of the wing. Now, so I'm sure I'm saying nothing new in this case. The point is why pretty much all aircraft are made in this way or are built according to a slight small variant of kind of structure. Well, it depends from the type of loads that the engine needs. The important thing to understand is that the aeronautical structures have the peculiarity. They need to be light because when you go and calculate the performance of the plane, you can see and demonstrate that the structural weight, the weight of factor in determining the performance. 1 kilo less of structure of weight is 1 kilo more. The 1 kilo more that can be used for useful payload or can be used to improve them in a way or another. So aeronautical structures need to be light. And as you can see, they are light because they are empty. I mean, this is the Mustang here is stripped of the skin just to see the thing, but below the skin, the aircraft is basically very empty. There's a lot of room available. This is obviously necessary to make the structure light, but to make a structure which is light and robust is obviously not easy. And it took a while, actually, in the design of the aircraft to get to the point of actually to understanding exactly how structures work. For example, this is the structure of a typical, this is Louis Blériot plane. This is structure of the typical structure of the First World War planes. Now, it was basically a truss, very similar to what was used in bridges at the time, and uh, with some elements that were to try to make it a bit more stiff. But that this works obviously because planes used to fly even during the First World War, but is definitely not the best. So which are so obviously the structure is made like this because of the type of loads the aircraft needs to bear. So which are the loads, the main loads that happen on a plane? You have so the main start from the wing as usual. So the lift itself is causing a structural load on the plane. The wing is producing lift. The lift happens on the wing. The lift happens along the wing. This means that the wing is pretty much bent upward by the lift. Bear in mind that there is no wing, no wing that is perfectly stiff, perfectly rigid. The all aeronautical structure undergo deformation under load. This is necessary because a perfectly stiff structure is also an extremely fragile structure. And because there's no deformation, you can demonstrate that if there's no deformation in the structure, the loads go up to infinity. So the wing is bent in this way. And this is the first type of load. The second type of load is the fact that the aerodynamic moment created by the aerodynamic forces on the wing, so the complex aerodynamic field around the wing, not just the and the so I mean the compounding of the lift, the drag, and all the other aerodynamic forces create a moment which is like this. So this effect is actually creates a torque in this way. So the wing is normally torqued, rotated, tries to be rotated in this way. So the wing must be capable of bearing the load, this flexion caused by the lift, and also needs to be capable of bearing the torsion caused by the momentum. And mind, the torsion is quite important. It is very important that the wing is stiff around the torsional axis because if the wing actually rotates, the angle of attack of each section of the wing changes, so the wing operates in different conditions span-wise. So this is a very important element. Coming to the fuselage, you have more loads. Well, on landing, you obviously have the load of the weight caused by the cap and the carriage by the gear. But also you have bending loads because the tail is either is generating lift upward or downward, and also you have torsion because when the vertical rudder is actually moving, it generates torsional moment around the fuselage. If this is the Mustang, so it's a propeller plane. Here it has some very strong bulkheads where the engine is actually attached, and the pull of the propeller goes through and it is actually transmitted to the structure. If it was a jet, it would be the engine in here on the back, and you will have some structural bulkheads, strong bulkheads, where the push of the engine is actually played. So let's go back to the wing because it's pretty much the most interesting part of the discussion. If we go, if you take a picture of a wing, no? So you have your bending moment like this, you have your lift. So let's talk about the lift. If the lift bends upward, the wing has to react in the opposite way. So the wing somehow has to generate a force which is the same and opposite as the lift. And this needs to be true locally for every small element of the wing because it must be in equilibrium. So all the forces on a single element must be in equilibrium. So you will have the aerodynamic forces, and then you will have the forces caused by the structure, caused by the structure itself that equilibrate those that pull, that push. To do this in a structure, okay, if you have a normal full structure, yeah, you will have some internal stresses that would go in the opposite way as the lift and would compensate. In the wing, which is a thin structure, this is a technical name, these are called thin structures. That's not very simple because that's not very simple. It's not simply like this because you have, for example, here and here you have the two spars, and here you have some surface that will be capable of generating an opposing force, but this is not enough because the wing is three-dimensional. So let us suppose that we are watching a section of the wing, which is actually here. So here you have a bending moment that bends the wing, and you need to react to this bending moment. This means that here, coming out of the wing and coming into the wing, you have some axial forces that compensate the lift. So if you look at from, for example, the front, this is the lift. So this is the lift. Look from the front. This is the lift, and this is the bending moment. To compensate that, you need to have an axial load, an axial stress in here, and an axial stress in here that generate an opposing momentum that opposes this bending momentum. So when you bend a structure like this, you also generate these two forces. And this is it is on one side, it will be like this. On one side, on the lower side, it will be traction, on the upper side, it will be compression. And this load is borne mostly by the spars. When it comes to the momentum, you need to generate enough torque that goes again to the momentum. Is the structures need to be capable of resisting by generating a torque that cancels the momentum on that specific point. And a thin structure like this does this in generating a flow. It's actually called exactly like this, a flow of stresses along the surface, along the external surface, along the plate, external opposing actually the aerodynamic momentum. So this is basically the way you want the kind of light and thin structures work. They transform transversal load like the lift into this kind of say traction and compression loads, and they transform torque, the torsional momentum, into a flow of stresses on the surface that compensates the momentum. So it's not like it was a bulk thing full of things that whatever you do on this, well, it pretty, yeah, pretty much resists to everything. These actually place the material only in areas where they can generate these kind of two forces, longitudinal forces, and this flow of stress. In this way, they are very light, they're empty, but they are designed exactly to withstand the aerodynamic load. This is something that took many decades to understand. Now well understood. And this is not true only for metallic surfaces. The composite, if you build this wing with composite materials, the concept doesn't change. You always need to do you need to use this kind of this concept is still valid. Okay, so this is the key concept to understand. The aeronautical structures are light not because they use light materials, but because they are empty, and they are empty because they place the material only when is necessary, only in a position such to generate exactly the forces required to cancel the aerodynamic forces applied and the inertial forces applied on the wing. For the fuselage, it is the same because the fuselage is pretty much the same. It's pretty much the same structure as we've seen, as we have seen before. I mean, the torque is supported by the bulkheads. No, it's absorbed by the bulkheads. Every bulkhead actually supports the torque, and the deflection loads are taken by the spars and the stiffeners or the stringers. Okay, so this is the intelligent thing in modern planes. Now, one last thing that I want to say, in modern planes, this surface of the wing, the panels that cover the wing, have also a structural function because they're integral part of generating this kind of load. Okay, and generally, almost all wings have a central structure like this, sort of a box, a torsion box, which is stiff in torsion and stiff in flexion. That pretty much gives the bulk of the structure resistance of the plane. There are two principles that are used to design this kind of structures that are called fail-safe and safe life. The first one is that if one element actually breaks, there is something else that is capable of keeping this flow generation, force generation going. Now, if you break the spar, there's pretty much nothing you can do. You're probably going to break. The wing is probably going to break. But if you break one of the stiffeners, one of the stringers, or if you break one of the ribs, or if you break just one of the stiffeners, just one of the ribs, just one of the panels, probably the structure would be a size that would be big enough and strong enough to withstand the break. The other concept is safe life, but we'll cover this in a minute. Okay, so the As we have seen, we have either traction or compression forces on the wing. For traction is not a problem because it's relatively easy to design for traction because well, it's stable. If you have this beam and you actually pull, well, it's going to get longer and longer depending on its module, but at some point above certain loads will break, and that's everything that happens. But if you compress it, what will happen is that it will buckle, and buckling is a very important problem in aerodynamic structure, in aeronautical structures. This is mathematically an instability, and this has been known. This property has been known for a very long time, and this is the formula, back to Euler, that allows you to calculate the buckling load um, of a beam like this. There's a similar formula for the plates that depend from the size, the aspect ratio of the plate, but this is the but as in here, as the longest is the beam, the lower is the load. For a plate, for example, the upper plates of the wing, obviously the longer is the plate, more streamlined is the plate, the more is the buckling to happen. So the point is, you don't have to design the structure just to withstand the load. You also need to design the structure to withstand this kind of instability, which is mostly buckling. Okay. Now, coming to, so we said that there is the first concept is the second concept that we didn't mention before was the safe life. And the safe life is the fact that the structure needs to be safe for its entire life. Meaning that there is a phenomenon that is called fatigue. That is, if you load a structure with loads which are below the breaking load, well below the breaking load, but you load it repeatedly, many times, what happens is that the maximum stress that the structure can withstand will go down over time. This happens because these small repeated stresses may actually, at a crystalline level, in small structural level, cause the creation of micro cracks that grow, and reduce the maximum stress. So this is the other consideration, very important, that needs to be made when you're designing a structure. The repeated load that the structure is undergoing needs to be considered to make a structure that is going to last long enough. When you hear that that specific aircraft has been designed with a useful life of 8,000 hours, 10,000 hours, so 15,000 hours, this means that it's going to tolerate fatigue for for that many hours. So the fatigue is not going to become relevant, it's not going to weaken the structure during that useful life. Okay? And to do this, it's mainly a problem of dimensions. It is the dimensions of the structure. If it is big enough, local stresses will be small enough to cause a very slow or of these micro cracks, and so the fatigue will not be important. So here we see for the metallic but fairly typical design of an aircraft joints. As you see, is relatively complex, and everywhere there is a joint, there is more material than everywhere else. This is in fact, all these holes, all these rivet holes are actually places where the stresses tend to concentrate and the cracks tend to grow. And this is, and it makes him strange, makes him counterintuitive, but the design of these joints is extremely important to guarantee that the plane has a useful life. That is exactly the one designed. Now, all of this is about metal. What about composite? Well, composites is basically the same. As you can see here, for example, type, this is a bit old, but this is the way a composite material, a beam of composite material is assembled. I don't know if you can see, but you see that these lines that represent the fibers of the carbon fiber or of the glass fiber, that they have different directions, no? And so they are juxtaposed in order to create homogeneous and create resistance in every direction, because these materials, obviously in the sense of the fibers, tend to have different properties than in perpendicular to the fibers, no? But when you build a composite structure, you actually want to make it sort of isotropic, no, as the metal is. Why it is used so much today? Yeah, because you can get 15-20% and today even more savings compared to a full metal construction. You can still build a perfectly functional full metal plane. It's still working, but obviously composite materials have a clear structural advantage, and this is all payload, that is extra payload that is available. And even if you build a structure with composite materials, and if you build a structure which is made with the mix of metal and composite material, this concept that we have seen before, the kind of forces, the way it is designed, don't change. You will have less junctions, for example. You can build a piece of composite that has a shape which is more complicated than metal, but you will need less junctions, but still the kind of strength, the concentration of stresses, the risk of buckling, and deflection, detortion, all this kind of thing are going to happen anyway. So this was a very, very, very quick overview of how aeronautic structure work. This is a subject that we can go on about talking about these subjects for quite a long time, and maybe we will do it. So I hope it was not too boring, because I had to put it together quite quickly, but I hope you have learned something new. And now we go on to the Q&A. We start with the Q&A. But before addressing the Q&A, when I published the message that there was going to be a live stream, a gentleman actually asked me what is a good book to start start studying. The Shovel is a decent book, but I believe there is a better one. I always suggest this book, Introduction of Flight. Is easy to find, is used in some university as a basic book. So this is university, is a basic book, but it's university level. And yeah, it covers all the fundamentals. So that is, if you want to start, that's where you want to start. Again, this is not sponsored, it's just me, just giving you a suggestion. And now let's move on to the chat Q&A. Sound quality on your voice is dreadful, data compression, miking, and so on. Sorry about that. That's one of the experimentation that I want to do. With a tube or a wood frame covered in fabric, you can take lots of damage to the fabric without compromising the structural integrity, part of why the swordfish fared well against the Bismarck. True, but the structure that you build in this way is tend to be quite heavy and not the best to support the loads. Actually, the planes where the structure support, where the surface, the cladding supports the part of the load work better. With a stress skin metal or fabric aircraft, damage to the skin of the aircraft might compromise the strength of the aircraft itself. True, as the same as before. No, if you just use a truss structure, it tends to be more heavier than a structure with the cladding. Which book is it? Introduction to Flight by McGraw-Hill, by John D. Anderson. I know it is used by in some US university. Hurricane also had a fabric tail and survived cannon shells from BF-109 because the fabric would tear off of the frame but not compromise the structure of the fuselage. Have you ever played DCS World? If not, what do you think about it? So I don't play DCS. There's a lot of people asking this. No, I don't play DCS. I hardly play video games. I generally don't play, let's say, video games. I like watching videos about DCS because it is accurate enough to be realistic. And I like watching the Grim Reapers because they are really entertaining. Actually, I like watching the Growling Sidewinder. And by the way, the Growling Sidewinder has non-realistic scenarios, but the nuggets of air-to-air combat tactics that he describes that he always mentions, are actually correct. So it is somehow educational, if you want. I am late. I'm sorry. I'm sorry. You will be able to this will remain available, so you will be able to see it. Have you thought about doing a video about the evolution of infrared missile technology and the tech used to counter-detect them? Yes, I thought about that. It is quite interesting. I mean, from an historical perspective, it's quite interesting because it's been very, very ingenious. I mean, pretty much all the weapons till the Sidewinder 9L were pretty much electromechanic systems, no? And yeah, they were really, really ingenious. Yeah, one day we'll probably cover it, but it is complicated because it will benefit a lot from animations that it's difficult to do. What is the commercial path that can be gained by developing a fighter plane? How does it help the nation apart from defense? Does it leaps to commercial sector? Can you give an example? So I suppose what is the effect of a make versus buy decision on a nation? So this is a political issue up to a point. So the what I can say is buy means has the advantage obviously that make the availability of the weapon is quicker, and the you buy something that you know that is already working, and so on. The problem is you become dependent from the vendor. So for all the spares, at least most of the spares, for most of the weapons, you become dependent from the vendor. So if politically you are happy to be, that's fine. So if a NATO country can buy from relatively safely from the United States, for example, from another NATO country. But if you are a country which is not aligned, for example, it may become a problem. The other the other problem of buying is that you need to acquire the foreign currency to pay the acquisition, and this is not um, normally this is not normally this is not normally the case. May not be easy because the only way to acquire foreign currency is with your export. So you need to export, being paid in foreign currency, and then using that to pay your import. Because if you buy a plane, is the import. On the flip side, if you build a plane and you don't have the infrastructure, well, you need to build infrastructure. This is going to take time. You will probably face quite a lot of failures, but I mean that probably if it is your first time, it's probably not going to be the first results are probably not going to be extremely good. But obviously you will be creating work, you will be creating, you will be building your own technology base, so you will be developing your economy. Don't know if I answered the question. Any plans for cooperating with Greg from Greg's Airplanes that could bring down the workload for both of you? No, we never spoke about that. Excellent, like always. Thank you. What did you study and what do you do for work? So I have a master in aeronautical engineering. Then I served for a time in the ground personnel. I wasn't a pilot, as someone believes. I served in the ground personnel of the Italian Air Force. Then I've worked for a short while in the aerospace industry. And then life brought me elsewhere. And I've been working on IT since then, and I'm still working in IT. I moved. Some of my customers working in IT have been the defense industry or the aeronautical industry, but that was a long time ago. I'm no longer in there. Boom jets, supersonic airlines likely benefit from military jet design. Yes, there is the interest around supersonic civilian aircraft is actually rising once again. So yes, obviously today we have the technology. It's no longer the time of the Concorde. What aeroelasticity and vibration consideration are important in preliminary structural design? They are paramount, in the sense that if there is something that can really stop a project and make it dead in the water, is actually a bad vibration problem, like a flutter problem, or I don't know if, flutter is, I don't know if you ever heard the term, but flutter is a type of vibrations that happen when the torsional characteristic frequencies of the wing actually are the same as the flexion characteristic, the flexional frequencies of the wing. So what then in this case creates a very complex vibration pattern that can really destroy the plane. So this consideration is paramount. You need to build, today it can be predicted with the structural design and computer assisted design. And so you can, so yes, it's extremely important. Before I just talked about static, the static part of the structures, but all the vibrations are, yeah, just another thing. Why are we still, well, that's very quick. I can't, why are we still designing fighters with pilots in them? Are we waiting on tech or stuck in tradition? Without the meat, you can save a lot of weight and cost, realize lots of performance. Because fighters with the pilots in there, with the brain in there, perform much better. That's the only reason. The artificial intelligence is nowhere near the capability of a pilot, despite that famous test when the artificial intelligence algorithm pretty much has beaten an F-16 pilot. That was really a rigged test. It was not realistic at all. Okay, the systems with the brain in there work much better. Drones can be useful, but some level of intelligence within the drones can be useful, but the brain of the pilot is still something that cannot be totally replaced. We will see a lot of a slow transition toward a mix of piloted and non-piloted vehicles that operate together. Slow transition, not quick. We will see a lot of drones, but drones that will be remotely piloted will not be autonomous. Drones that the level of autonomy that they have is to return to base autonomously if they lose contact, or they need to be piloted if they lose contact, stuff like that. Okay. The meat keeps the wars in check. If there is no risk to our men and women, we get reckless and start disregarding human life. A good point. There was a Star Trek episode that was very important about this. Which missile is a better long-range BVR missile, IM-120D or IM-54 Phoenix? The one fired by the most experienced pilot. Well, these still lack decision-making and problem-solving, communication, and jamming consideration, but there is a wingman and many other aircraft without pilot. U.S. Marine, K-Max, U.S. Navy helicopters. No, true. I mean, we will see a progressive shift toward a mix of piloted and not piloted. We see drones, which means remotely piloted with limited intelligence, but we will not see a replacement anytime soon, I believe. Not in my lifetime, I suppose. Is the Chinese J-20 based on the abandoned Mikoyan Project 1.44? They seem to be structurally similar and it would make sense if the Chinese bought the design from the Russian. No idea, I'm sorry. But it's an interesting point worth investigating. What do you think about fly-by optics that is using optical fires instead of fly-by-wire? Don't understand the question. If you mean if fiber optics in place of aluminum or copper cables, that basically makes no difference. Same thing. Carl Childers, fighter pilot here. Well, welcome. because you need decision making in real time on the spot with tracking, training, context, and analysis that doesn't exist in AI. Perfect. Advantages of moving leading edge extension on Sukhoi 57 PK5, better angle of attack control. No. Yeah, or yes and no. I don't know exactly. They may work in two ways, actually. The first, if they are deflected downward, they may be a way of actually controlling the flow above the aerodynamic surface. If they're deflected upward, they generate vortices all above the wing, and so it's a non-linear lift that may generate some extra lift that can be used during high angle of attack maneuvering. The way they exactly work, I am not so sure. It is one of the things that I am investigating. What do you think of the future of VTOL aircraft? Is it in the verge of becoming mainstream? Also, do you have an idea about S-500 defensive system's ability to detect fifth-gen aircraft? VTOL is... I don't think it's going to become mainstream because the weight penalty is still very important. Yet, modern technology makes this penalty lower than it used to be with the higher, for example. So, yes, we may see stuff like the F-35 more often, potentially F-35B more often, potentially. About the S-500, I don't know, obviously. If I had to guess, I think that they have something up their sleeves that they don't tell. But so we will never know. What do you think of the U-class aircraft X-47AB and the Lockheed U-class proposal and clever ways they reduce the RCS around the intakes, exhaust, and other part of the aircraft? No, they're interesting. They're interesting designs. They're really interesting designs. When you're free, drop me, okay? Do you plan to cover CAT's program from Aero India 21? There will be more about India. Obviously, I can't do it. It is obviously to all my loyal Indian viewers. I have done a lot about Indian programs. I will surely do more in the future. So it's not stop. I can't do everything about India. So because it would be disproportionate compared with the number of people watching the channel. No, I'm not abandoning the Indian defense in any case, in any way. What do you think about KC-46 program? No comment. What do you think of AMCA-TED still in development? Will you be able to catch up to other fifth-gen aircraft? Probably not, because it's the first try. 20 years time, probably 20 to 30 years time, probably yes. Do you play this? Yes, I've already replied to this. No. Perhaps the moving leading edge extension of the aircraft overall to go even deeper into angle of attack. Yes, it's exactly one of the points that I am trying to understand. Why do you think US has decided to continue with upgrading F-15EX? Is just a matter of cost and upkeep, or is it a matter of tactics as launching a lot of BVR missiles from a safe distance? So this point is very controversial as many want many people won't agree, and many F-35 fanboys will be quite angry. But I believe that stealth make sense. No, I believe the stealth doesn't make sense in any occasion. Adds cost and adds a aerodynamic penalty to the aircraft. That is probably not justified. So, good cells. I mean, uh, structures that are well designed, as the F-15, which is one of the best in traditional planes. I mean, 4-gen planes, it's probably the best 4-gen planes in the world. Are a safe bet for development. So, as usual, a mix of high stealth and lower um, non-stealth planes is probably ideal if you want to balance quality and quantity. Some experts say that the intakes on the Su-57 are insufficient to hide its engine, making its stealth less effective. Also, could you someday cover the Japanese Shinshin 5th Gen program? I have no. I'm not particularly sure about the intakes of the Sukhoi 57 and about the 5th Gen program, Japanese program. Yes, it's in the list. When there will be something more, a bit more details, I will cover it. I did a couple of times, but I don't like covering stuff which is still very early in development. It is, which is by the way, is one of the reasons that I'm not covering now the AMCA instead for from India, because they're just too early. They're just designs. You don't really know enough to say anything useful. Hey, would you be able to tell me more about the unusual shape of the YF-23 wing and why it hasn't been used afterwards? Because it was not particularly efficient. That wing was built like this for stealth consideration. It was, let's say, quite large, but the aspect ratio and yeah, I'm convinced that that wing wasn't particularly wasn't particularly efficient because it wasn't capable of generating the vortices that the delta generates. Probably. Never seen any simulation. Still didn't have the space that a delta wing it actually has. So I don't think it was a great wing. It was probably great for stealth, but not from an aerodynamic point of view. Can you go into issues that first-time countries manufacturers encounter when they put approved prototype designs into actual mass production? It is something I would like to cover in the future. As someone Demon Got Me says, as someone who works on the F-35 program, I am happy about the F-15EX. Every plane has a purpose. Good. What's your favorite fighter jet aircraft? Aesthetically, I love the F-104 Starfighter. As a concept, I love the Gripen. I think it is a lot of bang for the buck, and always aesthetically among modern planes. Yeah, pretty much everything in the flanker family is beautiful. Also, the Rafale is beautiful, but yeah, I'm sort of like a everything. There are really, really, really few ugly planes. Do you think that hypersonics will once be carrier-based or on a common thing in almost any air force in the future? Uh, for now, I see hypersonic weapons, not hypersonic vehicles. If you want to go beyond Mach 2, 2.2, 2.3, you start having a lot of problems that probably are not worth it. So regarding military aircraft sources of power, despite impractical nuclear power, would you say electric or hybrid will be viable, or say out-of-the-box source of propulsion? No, no, no chance. Current technologies, no chance. How's that Rafales are suddenly shot into the top, outpacing FA-18s and others many countries are buying or thinking of buying? Hey, it's another Gripen in the sense it's uh, it's a lot of bang for the buck. Is a jack of all trades, and normally you would say master of none, but he's very close to being a master of everything. Well, it's not stealth, but it's definitely a very advanced plane. It is a good choice. It is a definitely good choice for every country. It's very expensive. It is very expensive, but it is definitely a good choice for a country that doesn't have an industry. Also, the dependency from France is probably less invasive than the dependency from the United States or Russia or China. Um, it's the same also for the Gripen. No, dependency from Sweden is less invasive, even if the Gripen has many American or and British and Italian components. Should medium to low income nations pursue stealth like India and even to a lesser Pakistan and Indonesia, or should they focus on 4.5 Gen fighters and power in numbers? No, but well, this is a political decision, it's a strategic decision. That I said, if you want to develop a high tech industry, then just pursue the top of the technology. It will take a long time. It won't be satisfactory at the beginning, but in the long term, it's going to pay off if the policy keeps going. Otherwise, focus on something one step back is perfectly acceptable, and he still has. I mean, it's not that inferior to fifth generation. What country do you think will be the first to publicly use visible optical stealth on their aircraft? I think we will never have optical stealth, to be honest. There are some materials that create something like that. It could be used for ground forces, but with the current technology, I don't see this happening. Uh, um, I don't see this happening, honestly. Okay. Okay. So, what time is it? It's 41:20 to 10 here. So, well, so I think, let's see, maybe a couple of questions. Yeah, let's keep going. A couple of questions. Do you think orbital warfare ever be possible? Of course it's going to be possible. It is already possible. We just don't know anything about it. I'm pretty sure China and Russia and maybe India as well and the United States have already satellites in orbit, massed as reconnaissance satellites that are actually capable of maneuvering, having quite a high delta V, closing into enemies or opponents' satellites and knocking them out of the sky, or weapons like Indians and Chinese weapons from the ground that can actually intercept satellites. So yes, it's going to happen. Seeing men in space fighting, much less likely. Too dangerous for now. Are the latest fighter aircraft in danger of becoming so expensive and therefore small in number that they could be defeated by larger numbers of older, updated fighters? Well, actually, quantity has a quality in itself. I still believe that I actually believe and probably will tell you that there is much more in than the actual performance of the plane and the weapon systems. But to the overall effectiveness is the entire chain, the entire structure of an air force that determines the quality. And a key element, a key force multiplier is the training and the experience of the pilots and the commanders. Pilots that are great at piloting the plane but have no experience or are not particularly well trained in using them as a combat tool. Even if they have the superior planes, risk to be beaten by inferior planes. It happens many times. So technology is not always a win. Then everything else equal, you probably need quite a lot of older generation planes to beat, so say third generation planes to beat a fifth generation planes. You need 20 to 1 superiority or something like this. So it's probably not going to happen, but I don't believe it's ever going to happen that everything is going to be equal. It will never be like this. There will always be asymmetries that are key in determining the result of the encounter. Is there any technology you are looking forward to that we haven't seen yet, or major advances in capability over what is deployed today that you see coming in the near future? Well, direct energy weapons, hypersonic weapons, and say some level of artificial intelligence. And this is the thing. Other technology that we haven't seen, I can't see them. Honestly, it's probably too far. Technologies are a deal breaker. I can't see them, honestly. Why did the Euro Canards go for a single vertical stabilizer instead of a twin tails for higher angle of attack performance? Yes, because of the miracle of the delta wing, the vortices upon the delta, on the created by the delta wing are actually a stabilizing factor. So one single tail is probably enough. Will you do videos about helicopters? Yes, at some point, definitely yes. Last question, why not a Gen 4 jet on an F-22 airframe with newer electronics and less emphasis on stealth? Because the F-22 structures is built for stealth and it is 3 decades old. We can do better. We can use more composites and yeah. If we don't have any regard for stealth, you would build something which aerodynamically is a bit different. Okay, so yeah, I hope it was interesting. We spent quite a lot of time, more than an hour together. So thank you very much. Again, I hope to definitely being capable of resuming the normal programming next week. So thank you very, 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 very much for watching. I really appreciate you being here. We touched again more than 100 concurrent viewers, which is great. And okay, see you next time. Thank you very much for watching. Bye. Bye, bye, bye.